Node 2vec gives static graph embeddings, but many graph problems need context from neighbors at prediction time. You'll build a message passing GNN with PyTorch Geometric and see what changes. This is the workflow you'll know how to run when we're done, which trains on node features and edges and predicts node labels. I'm Professor Pi, teaching AI foundations with simple Python. Graphs show up in social networks, molecules, citations, and recommendation systems. The core challenge is simple to state. Entities link to each other, and those links matter. Traditional embeddings that ignore neighbors at prediction time can miss that context. Message-passing graph neural networks solve this by letting nodes exchange information with their neighbors during the forward pass. PyTorch Geometric is a compact library that gives message-passing layers and data containers, so you focus on model design instead of plumbing. Intuitively, a graph neural network turns each node into a richer vector by repeatedly asking neighbors for their views and combining them. Imagine a molecule where each atom knows its type and its neighbors. After one round of neighbor aggregation, each atom carries information about directly bonded atoms. After 2 rounds, each atom knows one step further. Strengths include locality and flexible structure handling. Weaknesses are over-smoothing when you stack too many layers and sensitivity to noisy edges. We will build a tiny end-to-end node classifier on a toy 4-node graph. The goal is simple. Show how a GCN layer mixes neighbor features. Add supervision to learn labels, train a compact model, add dropout for generalization, and then package everything into a tidy data object for evaluation. Nothing fancy, just enough to see how message passing changes node predictions and how to improve generalization before scaling up. Now we'll show a basic message passing operation. This snippet runs one GCN layer to aggregate neighbor features on a toy graph. We set a fixed random seed, so GCNConv has deterministic weights. The variable x holds 4 nodes with 2 features each, while edge index encodes directed edges in COO format. The call GCNConv22 constructs a PyTorch geometric layer that normalizes messages and mixes each node's features with its neighbors. Passing x and edge index to the layer produces updated embeddings in out that now reflect local neighborhood context. We report the average of node 2's 2 output features. The printed mean shows how neighbor messages altered node 2's representation. This demonstrates that even a single layer can shift a node embedding toward its neighbors and capture local structure. Next, we'll add labels and compute a loss before any training. This example adds supervision and measures how well the model classifies nodes before training. The tensor Y stores class labels per node, and train mask selects which nodes contribute to the objective. We stack 2 PyTorch Geometric GCNConv layers with a ReLU nonlinearity, yielding logits for 2 classes. The function cross entropy compares these logits to Y only where train mask is true, which simulates semi-supervised node classification on sparse labeled graphs. The loss variable is a scalar reflecting current misfit. Increasing hidden size in the first GCNConv typically lowers the loss by adding capacity, while decreasing it can underfit. The printed value is the starting training difficulty and helps you tune capacity early. Now we'll train a small 2-layer GCN end-to-end. This code trains a compact 2-layer PyTorch Geometric GCN for node classification. The class GNN defines C1 and C2 as GCNConv layers. Forward applies message passing, a ReLU, and then outputs logits. We construct Atom with a learning rate and weight decay. Then iterate epochs. Each step computes logits on the full graph, evaluates masked cross-entropy using only labeled nodes, backpropagates, and updates parameters. After training, we compute accuracy on train mask by comparing argmax predictions to labels. Increasing the learning rate speeds convergence, but may overshoot. Higher weight decay reduces overfitting at the cost of fit. The printed accuracy shows how well the model learned labeled nodes and gives a baseline for improvements. Next, we'll add regularization and a validation check. This example introduces dropout regularization inside a PyTorch Geometric GCN. The class GCNConv adds the parameter p to control the dropout rate after the first GCNConv, which randomly zeros activations during training. A new mask, valMask, selects held out nodes, letting us estimate generalization while training with Atom as before. We compute logits on the full graph, optimize cross-entropy only on train mask, and then evaluate accuracy on valMask by comparing predicted classes to labels. Increasing P strengthens regularization and can reduce overfitting, whereas reducing P may improve fit but risk memorization. The printed validation accuracy indicates how well the model generalizes beyond labeled nodes and guides your choice of P. Finally, we'll package the graph and run final evaluation. This code packages the graph into a PyTorch geometric data object and runs evaluation. The object data groups X, edge index, labels, and Boolean masks, so downstream code stays tidy and consistent. We set the model to evaluation mode to disable dropout, then wrap inference in no-grad for efficient, deterministic prediction. The call model data.x, data.edgeIndex computes logits for all nodes using learned message passing. We compare predicted classes with labels on test mask and take the mean to get accuracy. If you expand masks or features, data scales naturally. The printed test accuracy summarizes the final baseline performance on held-out nodes and gives a metric you can monitor while iterating. To map this toy example to a real project, replace the small feature matrix with your node attributes. Expand edge index to your graph edges, and set masks to reflect realistic train validation and test splits. The same message passing and evaluation flow applies. As graphs grow, batching and graph sampling become useful, but the core idea stays identical. Recap. What it is: a message passing GNN that updates node vectors by aggregating neighbor features. When to use it: when node predictions depend on local graph context rather than a single static embedding. One caveat: stacking too many layers can blur unique node identities and hurt performance. Next step: tune the dropout rate P and the hidden dimension to balance fit and generalization on your validation mask. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.